to present Nicholas Long from the Imperial College of London in the United Kingdom. And his lecture is on organometallic enhanced nanoelectronics and solar cells. Please.
Okay, thank you very much for the introduction, and it's a great pleasure to be at this EurASc meeting. It's my first meeting, and it's a first time to come to Lisbon. Beautiful place, and greatly enjoying the meeting and the weather. So for the next 15, 16 minutes, I'm going to give you a little bit of an overview of what we're doing in London. I'm actually a chemist, so I could be in the chemistry session or the materials session, it doesn't really matter. But in my group in London, I run a synthetic chemistry group. So today I'm talking about this bit, the area of perovskite solar cells, and how we're manipulating these materials. But the other half of my group, maybe I talk about in a future conference on medical imaging probes. So we know solar cells, and we've seen solar panels all over the world, increasingly important, and this is the area that's predicted to grow exponentially over the next decade as one of the reasons, or one of the areas that we can make a difference to sustainable energy. So these solar cells are great, but as you can see, they take up a lot of area, and actually silicon is relatively expensive to produce, and there could be other ways that we could make these things even better. So this is photovoltaic energy. Many of you will know this topic, so I basically won't go through too many details to save energy, save light. Sorry, go back. This pointer is sensitive. So basically, we are taking sunlight, energy harvesting, and converting it into energy. This is called the photovoltaic effect. And so the first generation of these materials are what we know at the moment, the silicon-based materials. So these are the big panels, but they're very efficient, but they're very heavy, and they do cost quite a lot of money to produce. So are there other alternatives? Well, of course, there are alternatives. People are looking at second generation using gallium arsenide type cells, semiconductor type of cells, but also this third generation. This is the area that I'm particularly interested in, which is where we're using more lightweight materials, more user-friendly, more earth-abundant materials to solve these energy problems, and producing cells within this area. So this area is dominated for the last 5 years or so by the emergence of perovskite. Okay, perovskite is an earth-abundant material. It can be found as a mineral, but also you can produce these type of materials very easily using, as I say, earth-abundant elements. There's no precious metals involved here, and they're finding uses for a whole range of applications. And the nice thing is that they have tunable band gaps, and they're very low temperature processing, manufacturing processing, so they can be prepared very cheaply. And so a lot of people are using these for a number of different applications. So we are particularly interested in solar cell devices, and for those in the field, and if you want to know more, there's this nice review in Nature Energy. These type of devices where various layers of material is deposited on each other, what we call a conventional and an inverted type of device, but you can see perovskite is the central material in the device, and there's conducting layers up and above the perovskite layer. So these are much cheaper than solar cells to produce, and here's just a quick comparison. So both of these give very high efficiencies, and the key thing here is the low production costs of the perovskite materials. So there's a lot of energy saving, not only because the materials are cheap, actually the energy you need to produce these materials is very cheap as well. So the key things we have to work on, though, for the perovskites are down here. So the long-term stability, that's not yet proven. So silicon has been around for many years. We know these panels will last over 20 years, whereas the perovskites are developing. The stability is not quite there yet. And the other thing is recyclability. We need to work on the removal of lead at the end of life of these materials. So perovskites involving lead are at the moment used, but people are thinking of ways to replace the lead. But there's lots of potential commercial value, and we saw the previous talk about TRL readiness, and I think this is quite early on in the perovskite area, but this will be an area to grow. So perovskites this is the problem with perovskites. This is a quick surface sketch of a perovskite, and basically this perovskite surface begins to degrade, and this is where we need to, what we call passivate. We need to add layers or chemicals that will help the passivation. This is the key question to answer for stability reasons. And people are doing this chemically, but also in materials sense, by trying to look at the Lewis base passivation, that's adding chemicals onto the surface of the perovskite that will add to the stability. Okay. So this is a collaboration that I started about 5 years ago with the City University of Hong Kong. And this is the collaborator, Zhong Wong Lu, is a fantastic collaborator over there. And he was the first person to really suggest that we could use some of our materials in perovskite solar cell production. And currently in the field, you'll see two types of perovskite, what we call a tandem cell. This a thin film perovskite, a single cell. Hopefully you can see this. Not very good, but better than the other one. So yeah, so we've got a single thin film perovskite, or what we call a tandem perovskite, where the perovskite layer lays on top of the silicon. So you have two chances, and this is probably where the field will enter commercially. So this was this chance conversation. So I'm an organometallic chemist. Those chemists in the audience will recognize this material. It's basically a ferrocene. It's an organometallic material, a collection of carbon ligands with a metal center that's iron. So these are relatively commonly found. They are relatively cheap to produce, and these things are tunable in terms of we can add different functionality around the organic core. And so the PCE, the power conversion efficiency, was the number here, and I won't go into too much detail, but there's not much chemistry here because I know this is not a solely chemistry audience. But these numbers were about our first series, just started just looking at some of our compounds in the lab, were already over 20%. And anything over 20% was quite interesting to the field. So we sent these to Hong Kong. My collaborator Zhong Long looked at these, and he said, yeah, these are good. Have you got any further materials? And so we looked around our lab, and for those in the audience, the chemists again will know this material. This is a compound we published in Nature Chemistry in 2016, and one of my students was trying to reproduce this material using this equation down here. And this is where serendipity, the beautiful serendipity of science comes into play. You know, she was making this is what she was trying to make, but this material next to it was a byproduct in red. This was a byproduct that she kept getting. So we had lots of this byproduct that we weren't doing anything with. So I thought, actually, looking at some of the groups on this byproduct, maybe this could be useful for perovskite. So we took some of this material that otherwise was worthless, we sent it to Hong Kong, and the efficiencies that Zhong Long was able to measure were over 25%. So this was really eye-catching because some of these materials had never been used in this field before, but also the numbers they were giving was over 25%. So we were lucky enough to publish this work in Science in 2022 because it was the first example where somebody had used an organometallic layer within this perovskite device. So you can see the perovskite devices have multi-layers, electron conducting layers, hole transporting layers, the perovskite itself, but the little, hope you can see it, the little yellow band here was our organometallic material that had not been added as a layer before. So this was the breakthrough result in the field to show that organometallic species could have a role to play. And you can see we've got very, very good efficiencies, but actually it's the stability. The stability after 1,500 hours was already about 98% of that initial stability. So there was very little degradation. And this combination enabled us to get the science paper published. And so we looked at, why is this happening? What's happening on the surface? And as I say, there's lots of details. You can have a look at the publication. It's been very popular in the field. We've already got over 500, 600 citations in 2 years. So it's really galvanized the area into thinking, how can we manipulate these layers? And we think there's the combination of the ferrocene, the movement of electron density, but also the perovskite surface. You can see these lead atoms are now being passivated, what we call passivated. They're being bound to by the oxygen atoms in our compounds, and that's helping the degradation. So these things have been looked at by other people as well, looking at, as I say, ferrocene. This is the organometallic material of choice. You can buy this material. It works quite well on its own, but actually we need to do the fine-tuning, we need to do the extra chemistry that we're doing to really have more of an effect. And so we've taken this on. We've made now not only a single species, but now we've made oligomers, so we've got a dimer here and a trimer over here. And so we can begin to make polymers of these materials. And this is published in Journal of the American Chemical Society earlier this year. And we were able to show, there's a lot of detail in this next slide and two, but the electropotential, this is the cyclic voltammetry, is beautifully stable. You can see what we call reversible waves. And its stability, it's showing you can tune where the redox waves come depending on how many ferrocenes you have. So there's quite a lot of material here. As I say, for completeness of time, I don't have too much time to go into depth, but the JAX paper will tell you more about this. But the key thing about this work was what we were able to do. We were able to take what we normally call a small area device and make it a large area device. Now, large area in this field is still only 1 centimeter squared. It's very small relatively, but the small area devices is where the field has currently shown, but actually scaling it up from 0.1 centimeter to 1 centimeter is quite difficult at the moment. But we're able to do that with our collaborators and still retain the efficiency that we had. So this is, again, really reinforced the initial publication and shows that this is actually transferable to other devices. And then just finally, in the last 2 or 3 minutes, the more recent work we've got is now to really work out what is making the difference. We have this amazing result. How can we capitalize on it? How can we tune the various derivatives? Do we understand really what is making a difference? So hopefully, again, maybe the chemists in the audience can see there's a subtle difference between the two compounds that we've made here. So we've got a carbonyl and then what we call an ester unit as well with an extra oxygen. And what that does, it tunes the electropotential of the materials. And hopefully you can see with this schematic, this is a publication we just submitted last week. Ultimately, we've got, over on the right-hand side, we've got the conduction band and the valence band of our device. So one of the materials has been designed to be lower than the conduction band, and the other materials to be higher than the conduction band. So we've got one of the materials is what we call electron-rich, and that actually is then inputting electron density into our perovskite material, whereas the other material is electron-poor, and so that's not able to tune the material and add to our efficiencies. Okay, so here is the slide that summarizes this. So basically, on the right-hand side, again, you can see very good efficiencies for this area, around sort of 24, 25%. But the key thing now is we're understanding more about our materials. We can actually begin to tune whether we have an electron-deficient compound, whether it matches the conduction band of our device, whether it matches the valence band of our device. Can we push the materials up and below that? The important thing as well, we've still got stability. So the substituents on the ferrocene are still what we call passivating that perovskite layer. They're preventing the defects happening over reasonable lengths of time, so 1,000 hours now. And at reasonable temperatures, we probably need to go that a little bit higher, but we've got systems that we can tune to various applications. So this is where we are right now. This is very much ongoing work. We're hoping to maybe start a small company, as the speaker beforehand. We need SMEs in this area. So Imperial College in London is pushing me to try and patent this work and start a company. But we're getting very good understanding of what our materials can do. Of course, there are many, many other materials that we could use. We're working on different types of materials. We need these to be certificated by places like NREL in the US and Fraunhofer in Germany to give us really international benchmarking of our materials. And ultimately, we need to begin to make bigger and better materials. So this here is a 5 centimeter by 5 centimeter panel now. So we're getting a little bit bigger. The efficiencies aren't amazing yet, but they're pretty good. But the more we do this, the more we're able to enhance that. And ultimately, we can look at more at other applications, not necessarily just photovoltaic cells, but photodetector area and the organic thin film photovoltaics that's not really developed because of lack of efficiency. We think our materials could have a role to play there. And finally, we need to be able to manipulate our materials. So one of the big things about this area, the solar panels we see in our fields and on roofs of houses, they're very big, they're very heavy, they're very solid. You can't really manipulate them. But if we can print our materials, and this is, hopefully you can see, this is a thin film. Let's see if I can do that again. So this is being deposited on a thin film of plastic. So this is in collaboration with Specific. This is a place in Swansea. So they're depositing our materials, very soluble, onto these thin plastic films, which you can roll up. You can put on greenhouses, you can put on top of cars, you can wear them on your back if you want. This ultimately, in 10, 20 years' time, will give us better capture of sunlight and actually make this whole solar generation, we think, a lot more versatile and applicable. Okay, so that brings me to the end of my talk. Thanks once again for the invitation, Arnando and Pierre. It's wonderful to be here. I need to thank the people who've done all this work. So my team in London is on the left, obviously. So Stephanie, Will, and Francesco. They are the chemists in my group who've been making materials. And then a fantastic collaboration with the City University of Hong Kong, with Zonglong Zhu, who you can see somewhere in the middle next to me. He's been the PI collaborating and making the devices with our material. So a beautiful collaboration that's really, as you can hopefully see, been very successful. So once again, thank you for your attention. And if there's time, I'm happy to answer questions. Thank you very much. Pick one. We talk after lunch if you like, yeah. But which one? Yeah. Chairman? Mr. Chairman, yeah.
I'm just wondering about the design principle for this fluorescent-based molecule. Is it primarily tuning the work function, or are there any other criteria you can use?
So, I mean, I think it's a good question. I think there's various things we're looking at. We're still learning about what is making the difference. So clearly there's the work function, tuning into the efficiency. As I said, one of the key areas is the stability. So in the perovskite area, efficiencies are pretty good. They're up there with silicon. It's the stability is really the problem. So actually being able to stabilize the perovskite is more important than getting more and more efficiency, if you like. So the work function, yes, is important, but I think actually it's making the devices stable over at least 1 to 10 years. That's really where the field is trying to develop. And so people looking at the tandem cells, which is silicon and perovskite, that's maybe commercially where the field will go into, but we think there's more advantage longer term with the single perovskite. Thank you. I'm happy to take some questions over lunch.
Thank you. So, thank you very much. Quite inspiring. So next, I have the pleasure to introduce Professor Big Joe Wang from the National Taiwan University of Science and Technology. He's going to deliver a lecture on value-added electrolysis for sustainable hydrogen production. Professor Wang?
Okay. First of all, thank Fatima kind introduction. It's also my great pleasure to introduce our recent work in this symposium. The topic I would like to present is value-added electrolysis for sustainable hydrogen production. Okay. Toward net zero emission, our renewable energy would increase dramatically. However, they are intermittent and also produce unbalancedly geographically. So once the energy produced more than the demand, how we can either storage the energy by electrochemical energy storage system, or just produce hydrogen or chemical by power-to-X process. That is very important for the future to net zero emission. So in this hydrogen economic, we can produce the hydrogen from electrolyzer driven by the renewable energy, and use this hydrogen to either produce the chemical originally from a fossil fuel, but we can produce the green chemical like methane or ammonia. And also we can produce the electricity based on this hydrogen, then back to water. So in this green cycle. So mainly we need to use this water splitting electrolyzer. So one side produce the hydrogen, another side produce oxygen based on the water oxidation. So however, if we want to compete with the current fossil fuel to produce the hydrogen based on this traditional electrolyzer, there are two scenarios here. The upper one is the electricity cost is higher, and the bottom one is the electricity cost is lower. And also follow the cost of the electrolyzer. So if based on the higher cost of the electricity scenario, even we reach 2050, the cost of the hydrogen is still much higher than produced from fossil fuel. Only if the cost of the hydrogen only $20 per megawatt hour, then to 2050 we can compete with the fossil fuel. But if with this, we need to wait until 2050 in order to meet this, to compete with the fossil fuel, how we can replace the fossil fuel application. So we need a radical change. We need to develop some technology so that we can have a radical change to reach this condition as soon as possible. So in my group, actually, we are working on this value-add power-to-X process. So instead of use traditional water splitting technology, once I produce hydrogen and as I work in evolution, we try to develop some redox pair so that we can simultaneously we can reduce the potential we need and also develop a catalyst to decrease the energy barrier. So that supposedly at the anode side we can produce valuable chemical and also reduce the energy consumption. But at the cathode side we still produce the hydrogen. So I will give you some example based on this development. So if you look at the traditional OER-based electrolyzer, just that if you consider only the thermodynamic limit, the cost of the energy consumption of hydrogen production per kilogram of hydrogen will be around 32 kilowatt hour. However, the current status is around 54. Even the DOE, US DOE ultimate target by 2050 is also set at 45 or something. Indicating its kinetic barrier is very high. It's very difficult to find good catalysts in OER reaction. Even if you can find very good OER catalyst, you still need at least 30 something kilowatt hour per kilogram hydrogen. But if we based on other value add oxidation process, then we can immediately draw the energy consumption to around 10 thermodynamically. But if we can find good catalyst, then we can easily reduce the energy consumption almost 1/3 of the current technology, and also produce the valuable chemical. So I will give you some examples. The first example is iodine oxidation. The thermodynamic potential, the current potential around 0.5 instead of OER is 1.23. So iodine is actually, you can see the application iodine is in like in pharmaceutical or in display industrial. The global market is quite huge. It's $1 billion US per year. So if we can produce this iodine and also produce the hydrogen, to reduce the energy consumption. That would be wonderful for this sustainable hydrogen production. So we developed a catalyst. I just quickly give the example. We actually developed many different catalysts. Like this example is the ruthenium tin alloy oxide. We can use this to reduce the overpotential dramatically. If you compare the OER base, this potential operated at like at 10 milliampere per cm square to produce the same hydrogen, but we need only less energy. Oh, too fast. Okay, we also developed this single atom catalyst. Just use glucose to produce the carbon sphere, then use CVD of the molybdenum chloride to produce the molybdenum single atom on this defect carbon. We use X-ray absorption and also TEM to confirm this is a single atom catalyst, and also use computation to confirm this defect. Single atom molybdenum can really lower the energy barrier for iodide oxidation. So with this, actually, we can this potential further reduce around 0.7 volt. So dramatically, we can reduce the energy consumption for hydrogen production. For other example, we in a single atom catalyst, it's very difficult to produce a high load in single atom. We actually develop a general approach. This we call electrochemically generate template, and followed by keramation. Followed by keramation. Then okay. So based on that, we can develop a general template. So by the keramation, we can replace and prepare different single atom with a higher loading, around 10%. But based on this metal PC, we can easily prepare different single atom. Like this example, we use palladium to do the keramine replacement. Then we can produce the dual single atom with the palladium and carbon single atom. Again, we confirm by X-ray absorption and also high resolution TEM. We can confirm we can get this dual single atom, then apply in this ethylene glycol oxidation. The main purpose is to do this ethylene glycol oxidation. We want to get intermediate species like glucolate, which with a higher value. So like in this example, we can get around 80% of Coulomb efficiency of the glucolate during this ethylene glycol oxidation. But at the cathode side, we still get the hydrogen, so that we can get hydrogen and also get glucolate at the anode compartment. The final example is, of course, this nothing to do with hydrogen production, but how we can use power to X to produce valuable chemical this we just produce dual single atom, this copper nickel single atom, and we perform a CO2 reduction. And interesting, we can get very high ethanol clump efficiency around 83%. So at the voltage at mass upon 6. So we try to understand what happened. So we perform this operando acid absorption to monitor the status of this single atom. If the potential higher than mass 0.8 is would at the single atom state. Now once lower than minus 0.8, some copper single atom will reduce to a copper cluster. Even further, then the copper cluster become bigger, but the nickel still remain the single atom status. I won't go to the details. So that's the reason if you can control at the dual, it still operate at a single atom state, you can get a higher cumulative efficiency of C2 product, ethanol product through this catalyst, this dual single atom catalyst. So finally, although I give you 2 examples to couple with value add another oxidation for hydrogen production. But in the future, we need a massive production of hydrogen, so we need more value add another oxidation. And toward net zero emission, we also the electricity percentage eventually will increase, so we need to learn how to use value add power to gas electrolysis. So no matter at a cathodic reaction or anodic reaction, if we can combine both, then we can produce valuable chemical and also the hydrogen. So some new system or selectivity efficiency or some durability crossover issue need to be overcome when you develop a new system. So finally, I would like to acknowledge the financial support from National Science and Technology Council and also the Ministry of Education and also the co-worker and the student working on the topic I present. And finally, thank you for your attention.
Now the next speaker is online. Professor Zhihua Wang from the State Key Laboratory of Clean Energy Utilization in the Zhejiang University in China. Okay, so he'll deliver a lecture on combustion of H2 and NH3 zero carbon fuels for the sustainable energy solution. Thank you, Professor Wang. We look forward to hear you.
Yeah, I think I have sent you the one video. So could you please play that video?
Dear colleagues and friends, my name is Zhihua Wang. I come from Zhejiang University. It's my honor to be here to give a presentation. Today my topic is combustion of hydrogen ammonia zero carbon fuels for the sustainable energy solution. This is the main content of my presentation. First of all, let's see the background. The total energy-related CO2 emission keep increasing, causing global warming and climate change. The United States, China, European Union, Japan are the biggest CO2 emission regions. Energy transition from fossil fuel to renewable energy become essential to achieve the target of carbon zero and carbon neutral societies in the middle of this century. Hydrogen is a kind of excellent energy carrier, green and carbon-free. However, the gas-phase hydrogen with very low energy density per volume, improve the pressure or liquefies is a good solution but the liquefaction temperature is quite a challenge. So combine hydrogen with nitrogen to synthesize ammonia could be a solution. This table shows the characteristic of typical fuels. You can see the gas phase fuels like ammonia, hydrogen, methane, they usually has a very low energy density per volume. But ammonia can be easily liquefied with room temperature and 10 bar. So the liquid ammonia can have a 11.48 millijoule per liter. The energy density was already accounting 1/3 of typical liquid fuels like gasoline, like diesel. That was very attractive. Compared with liquefied hydrogen, it's more economic. So the solution could be looked like this. The PV wind power could convert it to hydrogen through water electrolysis process. Though the hydrogen can be mixed with natural gas pipeline, due to the risk of the materials, just 20% of hydrogen could be allowed mixed with those natural gas. Then those gas can feed into the end users. The other part of hydrogen can be combined with nitrogen to synthesize ammonia. The liquefied ammonia can be transported through train and ships to the long-distance end users. The user can both burn those ammonia in gas turbines, engines, industry boilers, furnaces, power stations to generate power and heat without CO2 emission. Ammonia was first proposed to power the streetcar in New Orleans in 1871. In 1943, due to shortage of diesel during the Second World War, ammonia was used as a fuel to power bus in Belgium. The X-15 rocket plane was used ammonia as a fuel in 1960s. Then it stopped due to the low combustion efficiency of ammonia. In the year 2014, Japanese government launched a program to evaluate which method was suitable to long-distance transport hydrogen. They want to import hydrogen from Australia. They compare with liquefied hydrogen, organic hydrogen, and ammonia compound hydrogen. After evaluation, they think ammonia was the best way to transport hydrogen for a long distance. For the ammonia energy policy, in the October of 2021, the Japanese government announced 6 energy strategy plan. Ammonia energy was first introduced. By the 2030, hydrogen and ammonia will account 1% of Japan's energy consumption. In the November 2021, the South Korea announced high temperature combustion plan for ammonia and hydrogen. Ammonia will account 3.6% of the total country's power generation in 2030. By 2050, ammonia will reach 21.5%, and hydrogen will reach 13.8%. In this July, the Chinese government also announced the action plan for low carbon transition of a coal-fired power plant. They announced the first batch of a demonstration project should start in the 2025. 20% CO2 reduction per kilowatt hour should be achieved, either coal-fired with biomass, green ammonia, or CCUS. In 2027, 50% of CO2 reduction should be achieved, compared with the average CO2 emission level in the last year. So, ammonia, considered as a fuel, was taking a lot of attention in the community of combustion. So, both from the laminar flame to the turbulent flame, lots of work have been done. For coal-firing with coal, there was some companies already want to do some demonstration, like Japanese, the Heineken thermal power station. They announced in the year 2025 they want to burn 20% of ammonia in 1,000 megawatt unit. South Korea also do some fundamental research. The Chinese energy group testing the 40 megawatt small-scale industry boiler with 35% ammonia co-firing. Waneng Tongling power station with 300 megawatt unit running with 10% to 35% ammonia for 2 hours. that could be a good start to start the burning with ammonia to reduce CO2 emission. Next, let's look at the work, what we have been done in my group. First, let's see the hydrogen ammonia laminar burning velocity fundamental research. So for the typical laminar burning velocity, it's a very important parameter to study the fuel properties. Typically, people usually use those type of sufficient expansion bomb method. With this quickly expansion bomb, people can measurement the flame propagation speed. But we are on the Earth. They are always influenced by buoyancy. Ammonia was a very low reactivity fuel. The flame speed is just 1/5 of the typical natural gas. So you can see it quite greatly influenced by buoyancy. They cause lots of system errors. The heat flux method is another typical method suitable for measurement laminar burning velocity, especially for low-speed flame like ammonia. This method was invented by Professor Philippe de Gaulle in the early 2000s. What we have done is we updated the typical design of a heat flux burner. The original design is with 0.5 mm holes drills in the brass. We updated it with 0.3 mm holes insert with 2 thermocouples. We updated the burner head design with this flat structure easily for image taking. Secondly, we use fine structure to restrain the instability performance. The third one is we use more high temperature oil thermostat to overcome the buoyancy effect. At the same time, we designed and made a high pressure rig. We put the heat flux burner into the high pressure rig. The rig can holding up to 50 bar with pressure control, with cooling, with ignition, with the software designed by ourselves. So you can see with those high pressure rig and heat flux burner updated, we can obtain very good experiment data with ammonia air flame. So you can see the peak laminar burning velocity of ammonia is quite low, just 7 centimeters per second. But if you see the natural gas can reach 37, 38 millimeter. Hydrogen can reach 280. That's quite difference. Co-firing with ammonia with methane and hydrogen could be a solution to improve the reactivity and improve the flame stability. You can see with making with hydrogen and methane, the combustion the flame speed was reduced, especially with the increase of pressure. If you co-fire with syngas is typically composition of hydrogen and carbon monoxide. They can also be improve the combustion performance of ammonia. That's the performance with mixing different type of ratio of ammonia with methane and hydrogen. Alcohol could be also generated from fermentation, from gasification, or of biomass. Could be renewable, sustainable energy. So mixing ammonia with those type of alcohols could be also helpful. But if you see different type of mixing have different performance, if you normalize go to energy-based composition, those fuels looks very similar, just except hydrogen. Next part, I will talk a little bit about combustion kinetics work, what we have done. The combustion mechanism of ammonia was first proposed in 1979, was proposed to describe the fuel NOx formation reaction routes. But later we realized when you burn ammonia, the amount of ammonia is quite a huge amount. It's quite different. So the mechanism later in 1915s was more suitable to describe those ammonia combustion. So what we have done is we use those updated syngas mechanism, C1 to C4 mechanism, together with the updated ammonia mechanism. We combine those new mechanism. We named it a CU ammonia mechanism. This mechanism can be freely downloaded from my web page. This table lists the typical recent published mechanism. You can see both from a DTU, both from a crack, from Schweizer, from a Germany group. This is CU mechanism, it's from my group. San Diego mechanism from the United States, Konov mechanism from Sweden, Oxford mechanism from Japanese. Our mechanism was first published in the year 2020. You can see from the evaluation of ELTE group from Hungary, they found our mechanism was the top 2 performance mechanism out of those 18 latest published ammonia mechanism. Our updated version mechanism published in the year 2022, it was the best performance mechanism due to the latest evaluation from this ELTE group. Our mechanism updated the formation of N2H3 radicals, as well as updated some key parameters of elemental reactions. So the validation of our mechanism, you can see at a different pressure mixing with different type of fuel, they have good performance. We also validate the ignition delay time with pure ammonia mixing with methane, with methanol, ethanol, as well as syngas. They both have a good performance. NOx formation is a very important issue during ammonia combustion. They can reach several thousand ppm if you do not control the combustion environment. So with the help of kinetic simulation, we can help to find some good strategy to control those NOx. So the strategy for reducing NOx formation could use the stage combustion, or called rich, quench, lean RQL strategy. First with rich combustion to control the NOx formation, then use lean combustion to burn out all the leakage ammonia. Finally, we go to the conclusion. Ammonia could be a suitable renewable energy carrier for long-term energy storage. Ammonia can both act as fertilizer and fuel, and could be an international bulk trading commodity, can be both directly burned in existing engines, boilers, gas turbines, etc., or crack back to hydrogen and nitrogen, then used by fuel cells without CO2 emission. Challenges of ammonia combustion like low reactivity, low flame speed and stability, and high NOx emission. Co-firing hydrogen and ammonia with methane, gasoline, coal could be a good strategy to replace fossil fuel-based energy sectors with zero carbon fuels step by step. Both improve the combustion performance while utilize the existing facilities, and at the same time reduce the intensity of CO2 emission. Thanks for your attention.
My name is Yuri Gagotsi. Thank you to the speaker for the online presentation. And the next talk is coming from Professor Jihong Wang from School of Engineering, University of Warwick from UK. And she will be talking about the need of long-duration energy storage for the decarbonizing UK power grid and analysis of the potential of compressed air energy storage here. The floor is yours. Please proceed to the podium.
Good afternoon. Thank you for Academy of Sciences invitation to give me the opportunity to introduce the van technology. It's not chemical process, it's mechanical process, compressed air energy storage. All right, so my talk has 3 parts. Start from explanations on why we need medium and longer durational energy storage for achieving net zero or deep decarbonization. And the second, will focus on one particular technology, compressed air energy storage, which is suitable for longer durational energy storage, then followed by discussion. Okay. When we look at CO2 emissions from different sectors, power generation sectors is still a dominant sector and probably the highest emission sector. So to decarbonize the whole energy system and the power generation sector would be the very important part. So in recent years, we probably see a trend. And in power sector, we increase power generation from renewable energy sources, such as wind or solar. And also to decarbonize other sectors, for example, heating and the transportations, we're trying to electrify those sectors. That's also increase the electricity demand and make clean power generations more and more important. If you look at the world figures and also UK figure, you can see the rapid increase in renewable energy. With this increase, it generates a kind of a challenge. This already been mentioned by previous speakers. And we know from electricity, electrical power cannot be stored. And the power generation must be very close to how much we need. If this balance is broken, the whole power system may be in trouble and may cause blackout. So to maintain this balance, traditionally, we regulate the fossil fuel and to regulate combustion in the power generator, in the thermal power plant, and to really manage and watch how much we need and then to regulate to the generation. But now, renewable energy, wind and solar is not regulatable, is not dispatchable, is not controllable. So that makes this balance, maintain the load and the generation balance more and more challenge. So that's why in recent years, many research focus on how to develop new technology to maintain this balance with an acceptable cost. Energy storage becomes one of the focus because energy storage can provide an energy buffer. So when you generate too much, you put into the storage. When you need more, you can generate from storage to balance the power demand. So energy storage research developed very fast, and also the market prediction is really high. And we can see the energy storage become a very hot research topic, but when talking about energy storage, probably a first term generated our mind is batteries. So we can see a lot of batteries and battery storage plants and in place, in built around the world. It doesn't mean it's energy storage or battery for electrical vehicles, for mobile devices, and mainly for stationary. If you look at this picture, it's a 100 megawatts lithium-ion battery put in place and really trying to help with power generation, balance the power generation and the load demand associated with the solar or wind. However, battery, especially lithium-ion batteries, is not suitable for long-term storage. And in the future, if we get rid of all the fossil fuel power generation, and there's a big gap. For example, this picture shows the UK February-March 2024 demand and the fossil fuel generations. And this orange line is the fossil fuel from natural gas power generation. There's a correlation between the demand and the fossil fuel generation. If we get rid of all of this, we need something in place to replace all this fossil fuel. And that means we need some mechanism if the few days, if no wind, or few weeks, no wind, and we still have a secured power supply to home, to industry, to various sectors. And there's 28 independent study on various scenarios for Europe and the UK, different countries, and all indicated come to the similar conclusion. And the energy storage needed will rapidly increase. It's not linear, but exponentially increase when we have a high percentage of renewable in our power generations. So not just energy storage quantity, but also energy storage duration we needed. If we have, for example, if we 100% renewable without any fossil fuel in place, we probably need a seasonal energy storage. That means we generate in one season and be used in another season as a long-term durational storage. One study analysis for UK scenario analysis in 2035, even 2035, we have not, it's not the time to achieve net zero. We also need long-term durational energy storage. But when we look at the energy storage, we need this, but which technology would be suitable or come to market to perform these functions? And there are various technologies. In this section, I just concentrated one of technology, compressed air, that's related to our research. And in terms of long-term energy storage, there's various energy storage technology listed over here. On the right side, we have, I put in red color, those technologies are suitable for long durational energy storage. Certainly hydrogen is one of the hot topics and probably hottest topic today. And people trying to use hydrogen to say in the future hydrogen can become a kind of alternative fuel and also become a long-term energy storage to balance of energy system. And in this session, we already have 2 talks relevant to hydrogen energy storage. And so with those technologies, and if you look at the cost and the compressed air energy storage probably come to the in the position with the probably lowest cost compared with pumped hydro, and hydrogen certainly still developed, we don't know in the future, but currently the compressed air energy storage has the lowest cost. And also compared with other technology, when you increase the capacity, increase the energy capacity, the cost per unit energy will decrease. So it has an advantage. And that's why our research focuses on this particular technology. Compressed energy storage is a kind of easy to understand process. When we generate too much electricity, we use the electricity to drive the compressor to increase the pressure of the air and put pressurized or high pressure air into a kind of a reservoir. Store there, when we need it, we just release the air to drive the turbine to generate electricity. And for compressed air, this technology, there are 2 main disadvantages or weakness. One is low energy density. We use the compressed air, just the pressurized air for energy storage medium. Low energy density, that means if you need massive energy storage, you need a large scale of bigger volume of storage. And second is low round-trip efficiency. 12 years ago, when we start working on the technology, the round-trip efficiency is around 46%. That means if you have 1 unit electricity to be used for storage, end up only 0.46 unit electricity can be delivered. So with a low energy efficiency. So in our research, really trying to focus on these 2 aspects. And one is, if we need larger storage, do we have this storage and the low cost? Second, how to improve the round-trip efficiencies. And one of our major works started in 2012. It's funded by EPSRC, a UK Research Council. And we worked with the University of Nottingham, Loughborough, and the British Geological Survey. and focus on two typical large-scale technology. One is compressed air, and there is a high temperature thermal energy storage. And through this project, we worked with the British Geological Survey and to investigate if UK is a suitable place to use this technology. So British Geological Survey and investigate all the UK salt deposit conditions and mapped them with the wind resources location. So work with them. Okay, and they developed a kind of analysis method and algorithms, and then did the initial analysis. Through the analysis, the results very encouraging. Even they use 1% of salt deposit to formulate the salt caverns to store compressed air underground, and we can achieve over, few thousand or 10,000 terawatt hours storage. There are massive resources in the UK, and also there are very good geological location mapping with the wind energy resources. And so with this study, and also we did a further study, because currently all the UK natural gas and stored underground in the salt cavern. And if with the current power generation from natural gas, suppose one day we get rid of all the CCGT power plant, and all these caverns available for compressed air energy storage, certainly also for hydrogen storage. And then how much energy storage we can get, even with the current existing caverns, we can get over 700 gigawatt hours storage capacity. And also based on the current power generation system, we did some analysis and how this storage can operate if we suppose we replaced with a compressed air energy storage rather than the CCGT and the operation and the cycles. With all this study, we write papers and white papers, roadmaps, and report to relevant department and government. And now, I think UK recognize compressed air as a wonderful optional technology for longer duration of energy storage. And in 2022, UK supported 3 demonstration projects. And in addition, we look at the improved energy round-trip efficiency. I'm not going into details into various aspects because there whole process, there are many components. A wonderful piece of work we did is develop a software tool for whole system analysis. We made this software kind of open source. You can use a library to formulate the whole system to do the analysis, and this one's available, and so that's through the research. And also we participate one of the first large-scale such kind of a demonstration project led by Chinese Academy of Sciences. And so it's a 10 megawatts power plants. And in 2019, the plants commissioned and to connect it with the power grid achieved 60 to 63% round-trip efficiency. This is a remarkable improvement compared with 12 years ago, 10 years ago, 46%. But this year, and another power plant with 300 megawatts and in operation and demonstrated 72% round-trip efficiency. And also this plant use abundant previous abundance from the salt industry, and so with a low cost. So from all the research, this technology should be technologically proved is feasible, but it's very difficult to attract investment. And if we look at the UK for electricity balance, power system balance. That's a cost for per month over 100 million pounds. But for battery, it's easy to get into this market because, for example, the cost, if you sign a contract for generation, but on the day, from balance analysis, we don't need the generation. The power grid need to pay high price for people to not generate. And, but this can be used, battery storage is quickly store energy and release energy. But with the longer duration, the profit getting, with the longer hours, they're getting smaller, so difficult to attract investment. So our current research is trying to see how to make it more investable and trying to bring the technology from generation set of market to fast response, high value electricity market sectors. And the research focuses on to combine this wind power generations to increase the wind value, to bring the high value, and also a current project is trying to combine with the thermal storage to increase the power and the response speed to get into the high value market. Okay, so thank you for your time and finish my address.
We have time for 1 or 2 questions. Yes, please.
Okay.
I think they're recording.
Thanks, Yuri. Thank you for that very nice talk. Thank you for that very nice talk. Can you comment whether you believe this sort of technology is suitable for a grid-based system or better for something that is more local smart grid so that you can start looking for local net zero solutions rather than a global countrywide solution?
Okay, that's a very good question because in 2000, we come into this research that in 2005, we worked on the compressed air uninterrupted power supply. This research led to compressed air batteries for local, for small scale. Initially, they become the very good products and had a very good business, signed a lot of contracts, but market changed. The battery, the price start dropping and even 10%. So end up this product, the local and smaller scale, phased out. The company ceased their, their business, but still keep their patents, but then ceased. So really, it's a good technology may not win in the market. So technology must be market fit. So yeah, so that for large scale the same. If you invest on battery, you can invest on the small scale, low risk, and also all the battery in the UK storage investment, within 3 years, they can get their investment back because the fast frequency response market has a very high value, 10 times, 100 times than the capacity market. But for compressed air, longer duration, you cannot get into that market. You have very low response speed, not very low, few minutes, but that market need a few seconds. So, it's really trying to find the place to make it profitable and attract people who invest on the technology. But one day, who knows? Yeah.
Let's thank Professor Wang once again. And it's my pleasure to introduce the next speaker, who will be my good colleague, Aaron Friedcheck from Brandenburg University of Technology in Germany. And he will be talking about mechanically robust microchips for reliable and sustainable high-tech products. What can we learn from nature?
Okay, thank you very much, Yuri, for your kind introduction. And I would like to talk about sustainability in microelectronic products. And let me make a statement at the beginning. If we will be able to reduce failures in microchips, or statistically speaking, improve the reliability and increase the lifetime, it will be an enormous contribution to sustainability. Let me start with history. In fracture mechanics one of the most important fundamental papers is the paper from Griffiths in 1921. And this, he established the power of fracture mechanics. He explained experiments, he explained theory, but he also made a very, very nice forecast to molecular processes and to fracture mechanics on the micro and nanoscale. However, it took nearly 100 years until it was possible to go into in this field, particularly to have experiments to show this. By the way, it's an excellent paper, and I always recommend to my students to read this original paper from Griffiths. What is it about? The major message is that defects and faults in materials are responsible for fracture of brittle materials and for failures. That means if we have an ideal solution, then we have a very high fracture strength that we can calculate. In reality, all materials, all systems have defects, have failures. That means we have to live with failures. We know it from aircrafts, but it's also in single crystalline microchips. Also there we have to live with failures. And if you see this explanation, then you see on the left-hand side the energy release rate, which depends on the crack dimensions, on the strain in the material, and the Young's modulus. And on the right-hand side, you have the surface energy, which is the material's resistance against crack growth. That means if we increase the left-hand side, then the probability of crack propagation is increasing. So that means we have the conversion of elastic strain energy into fracture surface energy. That's what this expression is telling to us. Now, let's come to nature. We have selected one particular example. It's a mollusk shell, and this mollusk shell has several functions to fulfill. You can imagine that in the sea, in the ocean, it has to be particularly resistant against enemies, and it has to be resistant against stones, also material impact from outside. And nature has made a fundamental and amazing thing, because the outermost shell has a high stiffness, it has a high compression strength, and it has a high fracture toughness. That's a perfect model for engineered damage-tolerant materials. And now we are at the topic biomimetics. What we can learn from nature and which role miniaturized tests and high-resolution 3D imaging can play. And you know that natural materials, for instance, this mollusk shell or also our teeth, are usually hierarchically shaped structures, and they have very often a combination of several properties. In the field of mechanics, combination of high strength and high toughness. And in most of the cases, these natural systems outperform engineered materials. Of course, why? We know nature had a very long period of time to design such a structure in the evolution process, and we don't have so much time for our engineering process. And also the microstructure of such biocomposites is tailored according to the needs that nature has. For conclusions for engineering and mechanically robust systems with high damage tolerance, we need a better understanding of the design of the materials and the mechanical properties. And what we have to do, we have to determine local materials properties, and we have to understand the processes as a crack tip. We really have to go into the nanoscale. And what I would like to show is an experiment which is a combination of micromechanical test and simultaneous imaging using microscopy. Now, if I'm saying using microscopy, then we have different possibilities for microscopy. I think all of you know light microscopy. We know this from the middle of the 17th century, and Anton von Leeuwenhoek has drawn very nice images. These first microscopic images of living bacteria were the fundament, for instance, for Robert Koch to learn about diseases like tuberculosis. Then we know electron microscopy down to atomic resolution. Without electron microscopy, it will be impossible to understand solid state physics, material science, and also 2D microelectronics. And here the first experiment was done in 1931 by Ernst Ruska. But in between is a very new field. It's X-ray microscopy with a resolution in the lab in the range of 50 nanometers. First experiment by Günter Schmal from Göttingen at the synchrotron, 1976. But in the lab, we have the tools only for about 20 years now. And the essential point, the unique point is that we have a combination of high spatial resolution and object penetration. We can penetrate objects. That means X-ray microscopy is high resolution, non-destructive, and 3D. Okay, this is a scheme of an X-ray microscope, very similar to a light microscope. You have a light source, that's an X-ray source, you have the sample, and you have a detection system. But in between, you have particular focusing optics. It's a condenser which brings as much as possible photons to the sample, and it's a lens, because refractive processes do not work. We have a Fresnel zone plate, and the Fresnel zone plate is a diffractive optics with hundreds of concentric rings, and at each ring, at each zone, there's a diffraction process to focus. Now, very often, colleagues are asking me why it did so long until X-ray microscopy became an imaging technique. And I have two reasons for this. The first reason is there were always arguments against X-ray microscopy. And even Nobel Prize winner Ernst Ruska, he wrote that it will be very difficult or impossible to build lenses for X-rays because the refractive index is nearly 1 for all materials. The second half of the sentence is true, because if you see the complex refractive index in the X-ray range, delta and beta are very small. Practically n is 1 for all materials. That means refraction does not work. However, Ernst Ruska also directed the community in the wrong direction, because we should think broader. We can also focus X-rays, for instance, by diffraction. And then we have, for instance, these Fresnel zone plates, these hundreds of rings. But if we want to get 50 nanometer resolution, then the thickness of the outermost ring has to be about 50 nanometers and with a high aspect ratio. That's very difficult to make, and we needed for this technologies from microelectronics, and they were not available earlier. Therefore, X-ray microscopy is a very young technique. Let's come back to the mollusk shell. The outermost shell of the mollusk is such a prismatic structure, and there we have calcite. This is a crystalline elements, and then in between there is an organic phase. And we have done in situ indentation experiment in the X-ray microscope. Okay, here you see it on the left-hand side, and on top there is the microstructure of the mollusk shell before we did this indent, And then after the indent, you see in the lower scale, you see the cracks. And the crack is going through the calcite, and we have shown this with the TEM images, the crystalline structure, and then we have an amorphous phase where the crack is stopped. And it seems that this is a very general principle of nature, that we have a two-step process. We have the first phase where the crack is propagating along interfaces, and then in the second phase, the crack is steered into a region with high fracture toughness, and there the crack is trapped or stopped. So that means nature knows that we have to live with defects. Nothing is 100%. However, there are mechanisms that allow us to stop such microcracks. So this needs a composite between a high strength and high stiffness building block, that's the calcite, and a ductile component with a high fracture toughness, here an amorphous organic phase. So that means modern fracture mechanics in small dimensions, it's a completely new field where we need from the experimental point a miniaturized mechanical test, and we need non-destructive high-resolution imaging. And if we want to do experiments in situ, then this experimental technique has to be non-destructive. So, and I will show that it is possible to control, to have a controlled steering of microcracks into regions of with high fracture toughness, also for engineered systems, for instance, for microchips. Here you see on the right-hand side a schematic cross-section through a microchip. At the bottom, there are these 1 billion or so transistors, but then on top there are 10, 12, or 15 layers of copper interconnects. This is the design. And these copper interconnects, they are isolated by dielectrics. So if you have a 300 millimeter wafer and you want to select the individual dies, the chips, then you have to do a thawing process. And during this process today, it's not possible to avoid that you have microcracks at the periphery of the microchips. And there's a high risk, and this is really happen, that microchips are propagating into the active area of the chip, and then you have a catastrophic failure. What industry is doing, you see it on the left-hand side, you have at the periphery, you have so-called guard ring structures. And these are structures with a high fracture toughness. The goal is that cracks from the outside, here from the thawing process, are stopped at these guard rings. And why it is particularly important now? It is particularly important because the insulating material was originally in microelectronic silicon oxide, but in the previous years, more and more organosilicate glass and porous organosilicate glass is used to insulate the copper from performance reasons, because you reduce dramatically the dielectric permittivity. At the same time, you reduce Young's modulus by a factor of 10 or more, and then I remember to Griffiths, then you see here's the Young's modulus, that means the left-hand side becomes large, and the probability that the crack is propagating is higher. What we can do, we know that copper has a size dependence of fracture toughness. On the left-hand side, you see this is fracture toughness and this is layer thickness. You see at about 1 micron of thickness, it starts to grow. If you have a cross-section of a typical microchip from today, then you see most of the copper interconnects are much smaller than 1 micron. That means no plasticity of the copper. The dislocations are not able to move. So this is really bad for the fracture point of view and to stop. We have one possibility, that's the highest level. It's about 2 micron. You see it's already a bit plasticity, But the guarding structures, which I talked about, which is a particular structure in the chip, this has about 8 microns. And with these 8 microns, it is possible to stop the crack propagation. Here you see the experiment. We have the X-ray microscope. Into the X-ray microscope, we established a particular experiment. It's a double cantilever beam test, miniaturized, and this has these guarding structures in the region of interest. So here you see the chip, 1, 2, 3, 4 chips, in between the scribe line where the thawing processes happen, and in red, the guarding structure. And on the right-hand side, please, now the video. On the right-hand side, you see how the crack is propagating, and the crack is propagating into the chip. And here you see 2 different things. Here's the crack stop before the guarding structure, but if you increase the force, then also the crack is going further. Okay, and now on the right-hand side again, now it's 3-dimensional in tomography. You see again the crack, how it is propagating, okay? And if you have a 3-dimensional set, you see then on the left-hand side on which levels in the interconnect the crack is propagating. And you can steer the crack either to the bottom where the transistors are, that's terrible, or you can steer the crack to the top where the metal 12 is with 2 micron copper, or you can steer it into the guarding structure. This is what we are doing. And interestingly, you see here on the right-hand side on top, you see the energy release rate. You see it in the scribe line. I cannot mark it. On the left-hand side scribe line, then you see the guarding structure, and then you see the active area of the chip. And you see the guarding works. The energy release rate, it's practically fracture toughness, is increased by more than a factor of 3. Why it is now important to study further? Because it has to be as small as possible, because each micrometer of silicon costs a lot of money in microelectronics. So that means with this experiment, we can show, with this in situ experiment in the X-ray microscope, we can show that the energy release rate, the critical energy release rate, is significantly increased at the guarding, and we have a controlled microcrack steering into regions with high fracture toughness. That's possible. The learning from the nature is that this design of damage-tolerant engineered materials and systems, that microcrack steering into regions with high fracture toughness is also possible for engineered systems. With this, it is possible to minimize the risk and to have more sustainable solutions in microelectronics. With this, I would like to thank my X-ray microscopy team in Dresden and my collaboration partners at BESI, Helmholtz Center Berlin, and the Institute for Metallurgy and Material Science of Academy of Science in Krakow in Poland. And thank you very much for your interest in this talk.
Thank you very much. We have time for a couple of questions.
Great job. You take a lot of presentation about how to say nano XCT testing for the microcrack propagation. I was just wondering a little bit about the before propagation, how the microcrack initiation form. So you can use method to measure this initiation.
Yeah, let me start shortly with Griffith's theory again. Microcracks are particularly critical if they are not in the bulk, but at the periphery. This is also some experience from our usual life, from cracks. And these cracks are initiated by the thawing process when you have this wafer and select the individual chips. then the thawing process initiates microcracks. They are very small, in the range of, let's say, 1 to 10 micron very often, but if you have some stress in the device, then they are growing. And the stress comes particularly from the packaging process, but also from operation, if you have temperature cycles also in the microchips.
Any other questions? Let me ask a brief question as well. We're also using now NanoCT to test MXene materials, look at the fracture. And of course, the challenge is that we deal with very small particles, and we're trying to push the resolution to the limit. What do you think is really the limit, at least for the lab scale, not synchrotron NanoCT?
Actually, this I have not shown today. We are working on completely new X-ray optics. And with this, from the physics point of view, we should come in the same resolution range as transmission electron microscope, because wavelengths of the photons is in the angstrom range. From the engineering point of view, my opinion is that 10 nanometer will be realistic in the next 5 years. Further will be not easy.
Very good.
But we are working on this.
Thank you very much. Let's send the speaker once again.
Thank you.
And our last talk in this session will be delivered by Professor Shiliang Feng, whom you already see on screen. Unfortunately, he was not able to come here, but you will learn about building a sustainable future with organic 2D crystals from Professor Feng.
Yes, thank you very much, Yuri, for the introduction. I hope everybody can hear me, right? Yuri can hear me, right?
Yes.
Okay, great. Yeah, I'm really sorry that I have the missed opportunity to meet all of you in Lisbon, which I really wish to be there, but unfortunately we have an important event in Berlin, so I'm currently in Berlin. So anyway, I'd like to introduce a little bit of what we are doing with the organic 2D crystal materials. That we have been, that we have been developing this type of material for the future electronic, optoelectronic, but also some other applications. So here I'd like to come to the key issue of the semiconductor material, which have been rapidly developing over the last several decades. And at the early 90s, there are only 11 elements which have been normally useful for the electronic, like silicon, carbon, and the other related key elements. But this class of material have been very broadly established over the last 3 decades. Especially going to the 2000, there have been 45 elements, which can be potentially integrated as semiconductor materials, for the electronics. And this demanding have been further increased by the, thirst of society for the artificial intelligence, to my view, in the future. So this has been seriously creates a lot of problems, and the electronic waste is one of the largest problems. That you can imagine all the electronic you cannot be recovered, you recycled easily. Only 18% of the electronic material and package can be worldwide, collected, retrieved, and recycled. So most of them have been just burnt out, into the environment, and this created the different hazardous substance. It's unfortunately the case. And this is also due to the fact that the world designed for electronics, the fuel and the geological reach, it etched out, in the devastating shape and the colors. And this is used for BBC a few years ago to clearly tell that the world is not shaped in the sustainable way, environmentally friendly way. And this is what this symposium have been discussing here, how we develop a better environment, better sustainable future, and the electronic material, battery material are the key issues. So within the European society, that there's a graphene flagship project over the last 10 years, and I also been heavily key member in this graphene flagship. So we have been discussed about the graphene and the two-dimensional material, if they are sustainable or not. So graphene basically, has been already a lot of important applications and also a lot of important potentials going to the, the energy, composite material, electrolytic, flexible electrolytic, ink, conducting ink, but also to the membrane technologies. And the graphene flagship, we built up the team and we investigate, and the conclusion is pretty nice to tell that the graphene is a sustainable material because you can recover it, you can make it by the controlled way, by the synthetic strategy. So basically, it's possible to going green with the graphene materials. So this is the one positive thing. And on the other hand, that nowadays community have been very much going to new 2D material, beyond the age of graphene. And this come up with a lot of interesting material, like the 2D transition method dactylites, which are nowadays an important class of material for the topological material or quantum material, to the metal oxide, to the perovskite material is also very important layer material for the solar cells. And the X material, especially the magazine to be mentioned, that our chairman, is the father of the magazine, is the metal carbide nitride, with also very important class of materials. And since we are organic synthetic chemists, we are very much into looking for the organic version of the 2D material, like the 2D polymer, simple monopolymer, and also 2D covalent organic framework or metal organic framework, which can be made as a very interesting layer material down to monolayer level, which allow us to discover interesting properties. And the fundamental structures, which you can put the different layer material on top of each other to engineer the unique electrolytic, optoelectrolytic properties. So basically, we have been very much focusing on these organic 2D crystals, that we organic layer material, which have the interesting high conjugated structures and with the strong interlayer coupling that we are looking for to tuning the property of these type of materials. So the advantage of this material is that they can be synthetically controllable and tunable, because you can do the bottom-up synthesis, to tune their property, and you can have a unique electrolytic band structure for this material, and it shows the layer-dependent property, which is pretty unique for organic materials. And of course, data science, AI, have been very important tools, to facilitate the discovery of this material. They are predictable, they are designable, and of course, they have low carbon footprint, in a synthesis, which is a very good point from sustainable point of view. We only use a very limited amount of metals, even we don't need to have the rare metals. And they have a unique phenomenon and the properties, which are quite important. So like in organic 2D crystals, you can find a broader range of materials, ranging from the insulators with a large band gap to the semiconductors with a well-defined band gap, direct semi-metals, and to metallic material, which are highly conductive zero gap materials. So basically, you can find also almost all these material in the organic 2D crystals that we can, it's possible to make the copper material like copper 1, copper 5 with the insulator. So they have low electrolytic, they have low electrolytic building block. They have large band gap, but they also possible to have the semiconductor materials, which is with the beautiful, colorful of these materials. And also metallic state can be made with the 2D conjugated metal organic framework, which are the popular to realize the different metallic state. And the direct semi-metal, of course, remain to the material to be discovered for organic. So it is still only predictable, but synthetically it is not feasible so far. But I think I believe it's also possible to realize. So basically, it's possible to bridge all the gap of this material from the organic point of view. And of course, there's a lot of interesting property phenomenon to be explored, especially when we go into the Mori physics, topologic, and the quantum material point of view. But today, I'd like to show example about the application of such a material going to more climate change area or energy related area like energy storage and the membrane by using these very thin organic 2D materials. So the first, before we talk about the possible application and the exploration of their unique property, the first question is how to make such a material by controlled way. And this has been challenging in the polymer chemistry community over the last several decades. So here I will show about the on-water surface synthesis that we have been discovered over the last few years. And the idea here is that we like to program assembly of molecule on the water surface. So firstly, we spread the surface model layer on the water surface, okay? And this surface molecule is very organized on the water surface. And then we add the first monomers from water solution. They will be diffused to the water surface by pre-organization in a very good environment arrangement. Then we add the second monomer into the water solution, which is further diffused to the water surface. And on this water surface, under the air-water interface, okay, the molecule can polymerize with a very good reactivity. And they lead to the two-dimensional arrangement with a very highly porous structure, which is end up with the so-called to the polymer monolayer to fuel layer or organic framework materials. And of course, there are several design principles for this methodology. I will not go into detail. Basically, we need to design the monolayer, with a suitable charge. And we also need to design the building blocks, the molecules, how to be pre-organized on the water surface, which need to be guided by the monolayer, with a very good arrangement. And then the third point is we need a suitable organic reaction, which can be facilitated for the reactivity on the water surface, like the imide reaction or amide reaction, which are very popular chemistry in the polymer science, and also from other reaction like a Katrinski reaction, polyaniline chemistry. This also end up with the possibility to make the 2D polyaniline that can be very interesting in electronic materials. The carbon-carbon bond, like a Kolivagin reaction, but also the dynamic covalent reaction, like a thin double bond with the shift-based reaction, that all these beautiful structures can be made on this water surface down to monolayer to fuel layer level. And the first case is so-called polyimide, polyamide. So we use the negative charges surfactant on the water surface, and they can guide the porphyrin molecule on the water surface with the pre-organization. And we add the second monomer, either anhydride monomer, so they can polarize with the porphyrin molecule to make the imide bond or amide bond. And this end up with the very crystalline, crystal materials with the very thin layers. And firstly, we need to provide the structures. And this will show you the morphology, with the single crystals, after a few micrometer size, okay? And this with the hydrogen TM and the electron diffraction, which the last speaker just showed the beautiful, scheduling and the X-ray or the microscopy. You can resolve the structures, with a molecular level resolution. And from that, you can confirm that is a single crystal, with a very thin few layer materials. We have a unit size about 3 nanometers, which is very precision. And of course, we can also further push, to understand the structures, but also under different materials, like in this case, the polyimine, for example, which we can also make the few micrometer single crystal size. And with the TM, we can even go to near atomic resolution, with the very crystalline structures, and even allow us to go to the green boundary to understand the defects, like 3 membrane, 5 membrane, or 7 membrane, which are more defective structures, or basically the green boundary structures, to be probed for these organic crystal materials. And the more recent development with our TM collaboration partner, which show that we even can go to atomic level, like you can image the porphyrin molecule. So this is a porphyrin molecule. You can image the bond, this is a bending ring, this is a biphenyl ring, bending ring, and this is a single bending ring. You can image the molecule structures, okay, at a very high resolution level. So basically resolution can reach about 1.9 angstrom. And this is really beautiful and very clear proof that we have this well-defined layer materials, with a few layers. Okay, so then come to the possible application for this kind of ultra thin organic layer 2D materials. So one clear application is go to membrane, because they have very well-defined pore size. They have integratable charge functionalities, like positive charge or negative charge, and they have very ultra thin thickness, which is very important for the diffusion length. And this application today, I will show example about the osmotic pore generator and the sustainable battery that they can integrate this ultra thin membrane materials. And the first case is this charged organic 2D polymer crystals that we can make with this special chemistry, which Katrinski reaction, which I caught. We can make this nitrogen charged molecules, and we have content anion is a boron fluoride is an anion, and we can improve the structure by the X-ray and the TEM, for example. And each crystal size can be up to 120 micrometer square size, okay? So we like to use this membrane for the osmotic pore generator. So these are simple device structures. With osmotic pore means that you have the salt with a high density going to the low density, okay, and across the membrane. And the ions, in this case, is the anion need to penetrate through the membrane. And if you put the electric circuit, you can generate the charge. Okay, you generate the electricity through this device. Okay, and this membrane has a positive charge, and they have well-defined, pore channels, which allow the counter anion, like a chloride anion, to be selectively penetrate, and this can generate the current and voltage. Okay, so without the membrane, you don't have any current or voltage, but when you put the membrane, you generate the current and you generate voltage, and of course, we are dependent on the concentration gradient, between the left and the right. So basically, with 50 times, you can reach to the maximize the current and the voltage. And they have very good selectivity, okay, with this selective charge, with the chloride anion with 90%, and the chloride, the potassium selectivity can reach to more than 20 times, and this will end up with a very good reasonable pore density for the anion, with especially for the chloride anion penetration to make this device workable for these materials. Okay, then the next example, I like to talk about a battery device by integration of this ultra-thin membrane. And here, I like to talk about the lithium graphite dual battery. So we use the lithium as the anode and the graphite as the cathode, instead of the graphite as the anode, which people nowadays know about the lithium-ion battery, where the graphite is the anode material, but here we are using graphite as the cathode. And for the graphite cathode, we need the counter anions for the intercalation chemistry. Okay, so this boron fluoride is a very big anion, need to intercalate into this graphite interlayers, okay, to boost out the energy storage. And on the anode side is the lithium stripping plating process. So the problem for this intercalation chemistry with the large anion into the graphite is that you end up with the electron decomposition due to the larger anions, and also you have the cation solvent co-intercalation, which is a bigger problem. And this, the question is, how can we be more selective without going to have intercalation of cation and the solvent? Because these end up with electron decomposition. So here the idea is we put a membrane, ultra-thin membrane, which without sacrificing the energy density, but we can block the cation and the solvent. So with the only selective intercalation and transport of anions. And this is what we use this 2D polymer, crystalline thin film. With the large areas, we can make it. We can make a thickness with a few nanometer to 10 nanometer. So they have a well-defined classic 1D channel, and they have cation backbone, which is very good for anion selective. Okay. So we first evaluate the current, the voltage window. So they basically have the potential for the lithium up to 5.6 voltage, which is a pretty electrochemically broader window, very stable. They have very good diffusivity towards selective anions, with a very good anion transfer number. And from theory, we can model the transport mechanism. Basically, we can go through the wider pore channel. They can also go through wider interlayers. So both channels can be favorable with the more decreased energy barriers through the 1D pore channels. So which suggests that a very ultra-thin film is very good for that. Then we examine and make the point of failure device. So this is our device. We look at the specific capacity and also the Coulombic efficiency. So basically, without the membrane, they do not sacrifice with the capacity. They have very comparable, capacity or capacitance, and the Coulombic efficiency is very much enhanced with the protection of the membrane. Without the membrane, it's only about 90%, up to 40 cycles. But with the membrane protection, they are very stable. And this can be reflected with the point of failure device. With the protection membrane, it's very stable. Without the membrane protection, it shows swollen because of electronic decomposition. Okay, and this also can be reflected from the cycle numbers. Up to 400 cycle, we have electronic decomposition. with the membrane protection, they are stable up to 1,000 cycles, with 90% of capacity durability. And this also can be confirmed by the morphology of graphite. Without the protection, it shows the disordering. With the protection, it maintains the crystallinity. So the final example, I will also quickly talk about another device about the aqueous zinc batteries. So we use the zinc as the anode and use the metal oxide as the cathode. And the metal oxide cathode, normally you have integration chemistry with zinc ion. So the electrolyte, the aqueous electrolyte of zinc sulfate, okay? So what we want to improve here is the kinetics on the cathode, because zinc ion is relatively big. So would be good to have proton. And the zinc sulfide, the electrolyte is a little bit neutral condition, but they still have some potential of proton ions. So if we can have selective proton ion intercalate, we can increase the kinetics, of the device. So this will show the idea we put the membrane protection on the metal oxide cathode, and we like to have majority of proton ion for the intercalation. Okay, so we can increase the kinetics and also durability of this device. And this just show the membrane that indeed we find if we increase the thickness of membrane from 20 nanometer to 80 nanometer, we can enhance much of the selectivity of the proton ion towards zinc ion. So the zinc ion can be basically blocked if you increase the membrane thickness after 80 nanometers. Okay, there's no penetration of zinc ion or very little penetration, but the proton ions penetration is not so much a sacrifice. So basically you have very highly selective proton ion intercalation. So with this, we can get a very good Coulombic efficiency, with the proton transport. So with the proton intercalation chemistry, and also improve the capacity retention more than 80% up to 1,000 cycles, and we can still achieve very high theoretic capacity energy density for this device. Okay, so with this, I'd like to conclude my talk, and I of course like to acknowledge my group, for their important contributions, and also my collaborating partners, which I show here with the Kaiser, the Heine, but also partner from Dresden, like Aaron Fried, Chess, our last speakers, and the financial support. And finally, thank you very much for your attention. Thank you. Yeah, Yuri, I cannot hear you. Yeah.
On time, Xilang.
Yeah.
I hope you don't mind taking a question too.
Yeah, sure.
Thank you very much for nice presentations. So I think the artificial skin for electrode is very promising to improve the efficiency of the battery. And my question is, what's the main challenge to use this technology for the real applications, or how far to the real application? Thank you.
Yes, okay, very, very good question. I think there's two aspects for the real application. So the first aspect is the device itself. So when we talk about the aqueous energy storage device, like aqueous battery, there's also nowadays a lot of efforts from industry and the academic to push the technology. So they are not on the market yet. That's because of cost, durability, or many reasons to be optimized. But there's some spin-off company nowadays to push the aqueous energy storage device, like the aqueous battery on the market. So this will take some time, but they're the only way to go. And the second issue, I think maybe more your concern is about the membrane, what we developed, how can be practically useful to be integratable at the practical level. So basically, currently we are doing at the laboratory level, we can make an ultra thin membrane over, meter square size. But in the future, I think we will go to roll-to-roll process to make a larger scale production and to integrate this membrane for the real applications.
Any other questions? Oh, right.
Yes.
I think, Link.
Yes. Oh, Rafi, good to see you.
Yeah. Could you tell us what areas do you think will be scaled up appropriately going forward? Because we've had 10 years of the flagship project and materials. So where do you think the main trust will be for the first generation of these technologies to come through?
Okay, very, very good. So, Ravi, very, very good point. I think you are talking about the graphene flagship. So basically, the graphene flagship is mainly devoted to the application of graphene. So honestly, the support of graphene flagship for other 2D material are not that huge. So because the European Commission like to push the real application of graphene materials, And basically, I think the real application for graphene for the killer application is still challenging. So if you talk about electronic, or optoelectronic device, I think there's still some way to go. But of course, people move from graphene as a non-semiconductor material to other 2D transition metal dichelite, which had much more promising. So that's on the stage of the large area electronic demonstration by using the TMDC materials. But for the graphene itself, the current main application is to go to more composite direction. They are being used for as an additive for the battery or polymer composite for mechanical property, and also the composite material for concrete. So there's a company working on the concrete materials using graphene as additive. Of course, they use the few layer material graphene, not the single layer graphene. So these are the few current applications. And also there's a big application of graphene in the Chinese market is going to the mobile phone as the thermal conductors, to faster transfer the thermal conductivity. So we have a good market to my knowledge right now, and especially when we talk about the AI future application of electronic device for AI, the thermal management become more and more important. And I think this is a very good opportunity for graphene materials. Yeah.
Thank you very much. I think it's time for us to close this session. Let's thank Professor Feng and other speakers again.